Welcome everyone to the lecture about deep learning. So deep learning is a family of machine learning architectures which are based on neural networks, and they are called deep learning because typically they have multiple hidden layers, so they are deep in that sense. Most basic ingredients of this approach were in place by the last decade of the last century. However, currently there is definitely a revival of neural networks. This has been enabled by a couple of developments. One of them was the availability of large scale data sets, and the second one was the developments in hardware, specifically graphical processing units or GPUs, have enabled training at a scale that makes these approaches practical to use on these large data sets. And so the combination of these two factors has made this much more successful than it was in the past. And so the most common applications of deep learning are something like image classification, speech recognition, translating from one language to another. So these are the typical ways that deep learning would be applied. But beyond those classical applications, it's also applied in many different domains, and increasingly so. And so, what are the motivations of this particular approach? We can start with the curse of dimensionality. So many artificial intelligence tasks have extremely high dimensionality in the raw inputs. So if you look at some of the examples that I mentioned, such as image recognition or speech recognition, if you look at what the data looks like, these are going to be pretty pretty high dimensional inputs, in the sense that if you decompose an image into the pixels, then it's going to be millions or tens of millions of pixels that you have to deal with. If you represented each of those as a single dimension in the input vector, then we are faced with a very high dimensional task. Similarly, for speech recognition, and in that case, it's we have a signal from which we can extract some features. That signal varies over time, so the dimensionality here is more in terms of the time dimension. And so most classical machine learning approaches, such as simple linear models or decision trees or nearest neighbors, these type of approaches do not work well in the case when we have hundreds of thousands of dimensions or millions of dimensions. And so we need to project inputs to low dimensional feature spaces if we want to use these classical approaches, and that would require very heavy feature engineering. So that a little bit defeats the purpose of machine learning. If most of the work that we have to do, or much of the work that we have to do, goes into the feature engineering, then we're not automating that much, or the only automating the easy part. This is where deep learning comes in. Deep learning basically makes feature engineering irrelevant. It does feature engineering as part of the learning process. So in deep learning, what we have many levels of features that are learned, driven by the learning objective. So we have many of these hidden layers. These hidden layers encode some particular transformations of the input data. At each layer, there is a different representation of the input. We can think of those as features of the input in a representation, which makes it easier to learn to predict the outputs, and there is a successive hierarchy of those. Another way of thinking about it is that what we're doing is discovering a so-called manifold in which inputs are representable by few dimensions. So this picture that you see on the right in the slide, which is taken from the book Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Courville, that illustrates this idea of a manifold. So this is in here what we have is in principle two-dimensional space. In this two-dimensional space we have this pattern. However, you can see that this pattern is arranged or can be arranged on some kind of a curve, and the position on this particular curve, this manifold, then basically fully determines where in this two-dimensional space this each point is. So this two-dimensional data is reducible, or can be reduced to a one-dimensional manifold. So this idea, if we generalize it to high-dimensional input spaces, that's the idea behind it. And so we're going to start and talk a little bit about the multi-layer perceptron. So the multi-layer perceptron is the most basic type of neural network, and it is still an important module in modern architectures, even though modern architectures include many more types of components. But to get an idea of what neural networks behave like, what they look like, this is a good place to start. So a multi-layer perceptron, as the name indicates, has something to do with a perceptron. So a perceptron was an approach to learning that was introduced by Frank Rosenblatt in this paper from the late 50s, from the last century. The perceptron, a probabilistic model for information storage and organization in the brain. So the idea behind this work was that it was inspired by human or animal cognition. And so it was actually a very, very simple type of thing. What you see here is a schematic representation of what a perceptron looks like. So it's basically a weighted sum of a number of inputs. It sums up the inputs using some weights. So these weights are indicated here in this diagram with W1, W2, W3. There is also a weight which is not connected to any particular input, but it's just a so-called bias. These things are summed together. This is a weighted sum. This goes through a threshold function, and then we have an output based on thresholding this sum. So either it's going to be a positive or negative a class that we are predicting here. This is just a case using perceptron for the binary classification case, which is determining whether something belongs to one class or another. And so this is the most common scenario where you use something like a perceptron. And so this is the way it works. These weights are learned in some way. There is a specific way of learning them, specific to the perceptron algorithm introduced by Rosenblatt. But that is a separate issue. We will talk about learning in the context of neural networks later in this lecture. So let's go back to the idea of multi-layer perceptrons. Well, these type of perceptron-like units, these weighted summation devices are arranged into layers. If we arrange several of them into layers, then what we end up with is a multi-layer perceptron. So a single perceptron-like unit, sometimes known as a neuron, is a node in a network, and it's connected to other units via weights. So we saw in the simplest case, in the single perceptron, we just had the weights connecting the inputs to the unit itself. However, in a multi-layer perceptron, we will also have weights connecting units to each other. And so these neurons are arranged in these layers. They compute function compositions, and we will see exactly what that means in a bit later. So let's just clarify a little bit the terminology. So we have, this is the basic idea behind multi-layer perceptrons. Each of these circles indicate one of those, one of those so-called units, and we will divide them into layers. So we're talking about the input, sometimes called the input layer, and this in this case consists of two units. So there are two dimensions, but in general it could be any number of dimensions. Then we would have the hidden layer, which is connected via some arrows or weights to the input, and there could be several of those. In the most basic case, there is just one. There could be many, And finally, we have the output. In this case, there are two output units, so the output of this network would be a two-dimensional vector. And again, that is determined by the weights which go from the hidden layer to these output units. And so let's recap a little bit these concepts. So the arrows between units, they correspond to weights, or they indicate weights. The so-called activation of a unit is a weighted sum of the units with incoming arrows followed by an activation function. So in the Rosenblatt perceptron, this activation function was just a step function, like a threshold function. In general, this is some other type of nonlinear step-like function. The details do not matter that much for our purposes now. We typically, when we talk about neural networks and MLPs in particular, we will use vector and matrix notation to make these to talk about how information flows in the network. So let's have a look at an example here. So this is the network that we saw depicted before. We have the input, which now I indicated with the with X, which stands for a two-dimensional vector. Then there is a matrix W, which collects all the weights from the input to the hidden layer. And then we have another matrix, U, which in this case collects all the weights which connect the hidden layer to the output. And so we can using linear algebra operations, so basically just a matrix multiplication, we can just denote what this network does. So first of all, we by applying the weight matrix W to X, we compute this three-dimensional activation vector in the middle, which corresponds to the hidden layer. So we can think of the weight matrix of the weights which connect the input to the hidden layer as simply projecting this two-dimensional input vector to three dimensions, to the three-dimensional space which is used by the hidden layer. Then we have some function f, which is applied to each dimension in this vector. So this is going to be some type of nonlinear function. And then again, after this nonlinear functions was applied, we again do another projection with these, which corresponds to using these weights which go from the hidden layer to the output. We do another projection from 3 dimensions now to 2 dimensions and apply another nonlinear function g. And after we have done this, we end up with our two-dimensional output vector y. And so this makes it easy to talk about the information flow in such a network in terms of linear algebra operations. And so that's also where function composition comes in. We have these functions. We have a matrix multiplication with W, that's a function, right? And then we compose that with element-wise function f. By element-wise, what we mean here is that there is some function, for example, one of those step-like functions, which is applied to each element separately within the vector. And then we have a matrix multiplication with U. So the matrix U was used as a projection. That again is a function. And finally, there is a final function G, which again is applied to the output of all the previous function applications. So you can see that this network can be seen as the composition of 4 functions: the projection with the matrix W, element-wise F, projection with matrix U, and element-wise G. So why do these networks contain a nonlinear activation function? So when a layer lacks a nonlinear activation function, when it does not have it, it's equivalent to a linear model. And linear models or linear functions are limited. They cannot represent some needed common but crucial operations, such as, for example, exclusive OR, if you may be familiar with. So this is a relatively simple Boolean function, but a linear model will not be able to implement it, because a linear model in this case is just a weighted sum in practice. So even if we have multiple layers, but they are all linear layers, that may not be enough. And the reason for this is that what happens when we compose two linear layers? Let's look at what happens look at the argument on the left hand side here. So we have a function f, which is by which we denote the projection with some matrix w. Then we're going to define another function g. This is going to correspond to another projection with a function with a matrix u. So these are two linear functions, right? They're just projections with these matrices. There is no nonlinearities. So now when we compose these two functions and create and define the function h as a composition of g and f, then if we expand this, we will see that we will then have a multiplication of two matrices in a vector, right? U, W, and X, and we can simply collapse. We can multiply. We can do these operations in any order we want, because that doesn't matter for the result. And what we can do, we can simply multiply U with W. These two matrices, multiply them together, will give us another matrix. We can call it Z. And then you will see that the function h, which was a composition of the functions g and f, corresponds to projecting x with a matrix z, where z is simply our matrices u and w multiplied together. And so you can see that h is again a linear function. So what we have proved is that composing two linear layers together again gives us another linear layer, which simply uses a different projection matrix. So that shows us that the nonlinear activation function is crucial for a multi-layer perceptron to be able to represent nonlinear functions rather than just simple linear functions. And so this is a key property of MLPs. They use these nonlinear activation functions. Another interesting property to know about multi-layer perceptrons and neural networks also in general is this universal approximation theorem. So what this theorem says is summarized here, that a feed-forward network, so something similar to a multi-layer perceptron with the same structure where information flows in one direction, with a single hidden layer with a finite number of units and nonlinear squashing activation function, can approximate continuous functions with some particular restrictions to any desired degree of accuracy. So that is meant by approximator. So if we have any function that we want to represent, we can use multi-layer perceptron to do that. Given some of these conditions that we have here, so that makes these models very attractive, because in principle we know that they can do most of the things that we would want to do in practice, or at least so they can represent them. There are some caveats here. Namely, this does not mean that the parameters of a network performing such an approximation are learnable from data necessarily, or easily learnable, right? So we know that such a set of weight exists due to this proof, but we may not be able to convince our model to learn those from data. So that is a big caveat. And also, secondly, the theorem talks about a finite number of units, but it does not provide any bound on the size of the network in terms of those units. So it could be, exponentially large and as a function of the input, for example, and that would make it impractical to use. So let's talk a bit more about learning. So the parameters of neural networks, such as an MLP, are learned by minimizing a specific cost or loss function, and that is something that they have in common with simpler models such as logistic regression. And so there is a loss function, which is sometimes also called a cost function or an error function. That function quantifies how bad the model is doing on the current training data, how many mistakes it's doing, or what are how bad these mistakes are. So we typically want to reduce the number and the type of mistakes that the model is doing, and so we will try to minimize this loss function, and we do that in deep learning typically via some variant of stochastic gradient descent. There are many different variations that are currently in use. These have important impact on the performance, but in general, the idea is some kind of gradient-based approach where we compute the gradient of the loss function and then try to move the parameters of the model in a direction which will reduce this function. And so loss functions for neural networks are non-convex, meaning that they may have multiple minima, and so that means that the initial parameters that the network starts with, they matter. So it does matter where in the parameter space we start, because we may end up in a better or worse local minimum after doing this optimization. So this is something very special to neural networks. When we typically start with some random parameters, and different sets of random parameters will give you different results. So you can run the training process with different initializations with different initial random parameters several times, and each time the model would behave slightly differently, or sometimes radically differently, depending on the architecture. So that's something that makes it a bit challenging to work with these models often. So more about the how we do the learning. So there is the concept of backpropagation that you should know about. So we often talk about in deep learning about the forward pass or forward propagation, and that means simply computing the scalar cost of the network based on the input and the target and the weights. So what we talked about before, right? We just do these matrix projections, apply the element-wise nonlinearities, and in the end we get the output, and then we compute the cost or loss function with this predicted output, comparing it to the true output. So that is known as the forward propagation or forward pass. And now we need to compute the gradient of this whole computation with respect to network parameters, starting from the value of the loss, and so this is known as backpropagation, because we we do this computation backwards in some way. So once the gradient is computed, we can use it to update network parameters using something like stochastic gradient descent or a version thereof. And so backpropagation it's just a funny name, but it's basically just a chain rule. So of calculus, you're familiar with the chain rule. The chain rule tells us how to compute a derivative of a function composition, and we have seen that something like an MLP or a neural network in general is a composition of a number of functions. So if we let's have a look at the very simplest case. We're composing two functions. If we denote the derivative of f as f prime, then the chain rule is defined as follow. The derivative of the composition of f and g is the composition of the derivative of f with g composed with the derivative of g. And so we can, this is for the case of two functions, but we can of course do it recursively and then compute for any number of functions that we want, and if we do that, then that is what is known as backpropagation. And so there are some technical challenges with that, but conceptually that's what is happening. So how do we do that? Do we do it like with a pen and pencil? Well, no, we use something called automatic differentiation, which is a generalization of backpropagation to not only MLPs but any type of architecture. So there are software toolkits which implement linear algebra operations and other differentiable operations which support automatic differentiation. And so they can do this backpropagation pass. They can compute the gradients of our computations automatically without us needing to actually tell how to compute the derivatives of our model. So there are a number of software toolkits, as I mentioned. The two most well known are called PyTorch and TensorFlow. There is also something called a toolkit called Keras, which is builds on top of TensorFlow and implements common deep learning building blocks. So this is a good toolkit to start with, playing around with deep learning, because that makes it all very straightforward. Also, something similar can be done in PyTorch. There are some predefined modules and functions which allow you to quickly build neural network architectures. And both of these you can use in Python, so PyTorch and TensorFlow, including Keras. And so, so in the more general view of deep learning, that it simply corresponds to a differentiable programming paradigm. So deep learning goes much beyond MLPs as such. What you can see here on the right is a sketch of the architecture from a paper which was very important a few years ago. It's called "Attention is All You Need." So I don't want to go into the details of that particular paper and that architecture, but you can see that you have all of these different modules which are connected with some arrows. So they are trying to basically depict a particular program that this paper implements. And this program is called the transformer nowadays. They is known as the transformer, or at least the general type of programs known as the transformer. It's a quite an important component of many deep learning systems. And you can see that it has these different modules like feed forward, add and norm, multi-head attention. All of these things are basically, you can think of them as subroutines or functions in a programming language or in a programming language library. They just happen to be all differentiable, and most of them happen to have learnable parameters. And so modern deep learning architectures that simply consist of these different modules put together via the way that we would normally do programming. We just program with different components in a modular way, in a compositional way, and the difference is that these contain learnable parameters and that they only use operations which are differentiable, and thus these learnable parameters can then be updated using something like gradient descent. So that's, I think, a view of deep learning that makes it much closer to regular software engineering. And so I wanted to briefly discuss one particular case study, something that I have, together with other colleagues, I have been working on before, to just illustrate how modern deep learning is applied to different problems. In this particular case, we're going to be talking about a visually grounded model of spoken language. So what we are dealing with, we want to, in some way, simulate one important aspect of how human children learn language. They typically are exposed to people talking. People talk to them. People talk among themselves. When they are in the presence of children or talk to them, they often will refer to whatever is in their environment, whatever the children can see and touch around them. And so, to simplify it a little bit, we can use a data set where we have some speech signal, which is somehow correlated with an image. And so we have a visual scene. In this case, there is this image, and someone may be describing it with a spoken utterance, saying there is a bird walking on a beam. And so if we have a data set of such pairs of images and spoken utterances, and this is a large data set, then we can try to learn something about language. We can try to learn to understand and build a model which learns to understand language from the correlations between these two signals, the audio signal, the speech signal, and the visual signal on the other hand. And so, in this case, what we're doing is it's a bit different than a typical machine learning scenario where we have where we would normally be doing some kind of simple classification, maybe classifying images into dogs and cats. And here we have something which I refer to as weak supervision. So the scene itself needs to be understood in the first place. We don't really, a priori necessarily know that there is a bird in it. That's another thing that we have to learn to do. And also more importantly, maybe the correlations are noisy, so we can speak about things which are not present in the scene, and we usually speak only about a subset of what is present, and the same is true about these spoken descriptions of images. So people may mention some of the things but not others, or so there is a signal, but it's a relatively noisy and not weak signal in some way, but we still would want to learn from it. So what we will try to do is to project this. Use deep learning components to project the speech signal and the image to some kind of a joint space. So you can think of it as some hidden activation vector that we are going to be moving towards with these. We're going to be placing our utterances in the space, and our images also. And additionally, we also try to encourage certain structure within that joint space, such as the images and utterances, which are connected in the sense that the utterance describes the image. They are going to be moving closer together in that space. So these two vectors are going to be more alike. These two hidden vectors are going to be alike. And pairs of images and utterances which are not talking about this, which are not semantically connected, where the utterance does not describe the image, they will be pushed further away in the space. So in this example, if we have the image of the bird and the utterance bears play in water, they will be pushed further away. That is going to be the idea behind our loss function. We try to design a loss function which is going to encourage the vectors in the hidden semantic space or joint space, where we're going to try to make them far away from each other. And on the other hand, the vector corresponding to the picture of the bears and the utterance about the bears, we will try to move them closer together. This is indicated with the color of the arrows. So the green arrows are meant to indicate that these two objects should be closer together, and the red arrows should be further away. So this is our loss function that we're going to be using. And so how are we going to do this projection of these input images and input utterances into this joint space? And so we will use a number of components. Starting with the image, what is depicted here is something which is a little bit similar to an MLP, but it has some restrictions on the connections, and that's known as a convolutional neural network. So with a convolutional neural network, we will process this image, and it will we will project it into some space. In this case, we are using in this particular paper and a convolutional neural network which is already pre-trained on an image classification dataset. So that corresponds a bit to the fact that children, when they start learning language, their visual system is already working to a large extent pretty well, so they can recognize objects and so on. So we also kind of doing it a little bit like that. We use a convolutional neural network which already understands images to some extent, but we're not using any labels or any these labels that I have here, boat, bird, and boar, and so on. They are only used to train the model, but we don't use them to train the convolutional neural network model, but we don't use them in our own model of spoken language. So we discard these labels. We only use like the internal activation of this model as a representation of the image, as a projection of the image. And then the speech signal, we start with some speech features, such as the spectrogram, which is depicted here. We pass it through a one-dimensional convolutional layer again, which is something a bit similar to what is depicted on the right-hand side. And after that, we use some other components. You can see them depicted with this little squares, So the squares correspond, connected with arrows, they correspond to recurrent neural networks. And recurrent neural networks are a type of neural network which are meant to model something evolving in time. And there are 3 layers of those recurrent neural networks in this particular picture. There could be more. And so finally, we combine the representations at the different time steps together with some kind of weighted sum, and that is our representation of the utterance in the joint space. And after we've done that, we can compute our loss function based on this idea of moving the vectors together or apart, depending whether they are matching or mismatching. And we can update the weights of this model and learn in that way, and then evaluate what it has learned, for example, by giving it some new utterances and asking it to find images which are similar to which would correspond to them, and measure how well it's doing it. And it's able to do it reasonably well. So in that sense, it does capture something important about language, and we can think that it is able to simulate one important aspect of how we as humans acquire language. So to summarize what we've seen in this lecture, we've seen that multi-layer perceptrons are the most basic neural networks, and they consist of perceptrons-like nodes, or sometimes called neurons, arranged into layers. And then furthermore, that deep learning is a type of programming paradigm which relies on differentiability, and that differentiability allows us to compute gradients and thus to automatically learn program parameters. These are the most important takeaways from this lecture. Thank you.